Hello, welcome to another Cosmology talk. This week we have Mateja Gosenca, who is a postdoc at the mighty University of Auckland, and Bodo Schwabe, who is a postdoc in Göttingen. So this is the first joint talk we're going to have here, which is a nice experiment. Technically, I've offered this to everyone, but these two are the first to actually accept. Today they'll be talking about a code and code paper that they very recently released called AxioNyx, which is the first, I think it's the first, public code that can do both simulating of ultralight axions in AMR and cold dark matter at the same time. Thanks, Mateja, and thanks, Bodo. Do you want to start off by briefly telling us about the work in the AxioNyx code?
So in this paper, we present the new code for the simulations of fuzzy dark matter. It's called the AxioNyx. Fuzzy dark matter is by now probably one of the common candidates for dark matter, and it has extremely light particle, typically of the order of mass of 10 to the minus 2 electron volts. It's modeled with the Schrodinger Poisson equation. So this is the idea that you have a scalar field, which then evolves due to the Schrodinger equation and Poisson for gravity. Our code, like Shaun mentioned, has an adaptive mesh refinement, which allows you for really increased resolution in the regions of interest, while still keeping the main grid simulation relatively cheap, because it doesn't refine everywhere. So it only refines in the regions where, for example, density is really high. In other words, this has a high dynamical range. The code is based on a publicly available CodeNyx, which also has a lot of infrastructure for other astronomical things such as baryons. And so we employ this code to the simulations of mixed dark matter, mixed being one component being the fuzzy dark matter and the other component being the cold dark matter. And the cold dark matter is, on the other hand, modeled with n-body particles. And we also show some results of these mixed fuzzy and cold dark matter simulations.
Cool. So you briefly mentioned that Nyx can do baryons. Is that something that's in the near future for AxioNyx as well?
Hopefully, yeah. We're thinking of including this, but there's some features we'll actually have to add, so it's not just something you can use out of the box.
If people are remembering this talk a couple of months from now and there's only two things that they can remember from the whole talk, what two things would you want those to be?
Besides the fact that we have this very powerful code, which is publicly available and has adaptive mesh refinement, on the large scales, we confirm the Schrodinger-Vlasov correspondence, which basically means that our outskirts of halos behave as if they were really just cold dark matter halos. So the density profiles have exactly the same shapes as they would in cold dark matter halo. And we recover this for many different ratios between the fuzzy and the cold dark matter. And on the other hand, in the centers of halos, fuzzy dark matter is known to form these solitons. A soliton is like a stationary solution with the flattened density profile in the center. And we recover solitons for as little as 10% fuzzy dark matter component. But if the ratio is higher than that, so we run a few simulations where we increase ratio, then the solitons that form inside the halos are more massive. They have higher densities, and because of that, they're also more compact. So a more massive soliton has a smaller radius, and they also have higher velocities. So the central regions have higher velocities.
Why did you do this? So I guess in the context of why are axions interesting, why are ultralight axions interesting, why was AMR not something that had yet been tackled? Do you want to kind of go into the background motivation? Why should the cosmology community care about this paper?
Yeah, in terms of the code and of AMR, I mean, there are other codes in existence, quite a few by now, that have adaptive mesh refinement, but none of them are or were publicly available at the time when we started this project. So in terms of the code development, we just wanted a code that we ourselves can use, but then also share it with the community. So it's like a bit of a service to the community as well. In terms of motivation for the mixed dark matter, the axion particles are actually, theoretically, they can be produced over many different masses. So that there's even this idea of the axiverse, which kind of predicts a continuous mass spectrum with particles with many different masses. But astronomers usually care about the so-called ultralight axion, which has 10 to the minus 22 electron volt mass. And that's interesting because the de Broglie wavelength that corresponds to this is actually at the kiloparsec scales. And that gives like interesting, possibly observable features in the universe. And then there's also the QCD axion, on the other hand, which is quite strongly motivated from theory. And that has masses of around 10 to the minus 3, 10 to the minus 5 electron volts. And its wave-like structures would appear on much smaller scales and would not be observed. And therefore, the QCD axion really behaves like cold dark matter. So when we simulate the mixture of cold and this fuzzy ultralight dark matter, this could also be viewed as a combination of the QCD axion and the ultralight dark matter. And as far as we know, this is really the first attempt to sort of make more realistic simulations. Although it's only two components, it's still more realistic than just having one particular choice of mass for the axion particle.
And I guess as soon as the mass of the axion gets like above 10 to the minus 19 or 10 to the minus 18, it's going to be indistinguishable in your simulations from cold dark matter anyway. So it's not like you need to simulate 10 or 11 or 12 different types of dark matter for all the different masses. It's mostly going to look like cold dark matter, and then...
Yeah, everything that's heavier behaves like cold dark matter. In addition to that, there are also by now quite a few constraints on the ultralight axion. Coming from various different observations, and having like a mixed model with two components also relaxes those constraints, so they're not as strong.
Yeah, and I guess in the visible sector, there's not one particle. There's protons, electrons, neutrons.
Yeah, so there's no reason to expect that dark matter would have one only particle.
So the next question is then, what did you do in the paper? Do you want to go into the details about what is adaptive mesh refinement? How does it work? What are some of the results that Mateja has been hinting at?
So yeah, this is also the title of that paper, in case you want to check it on the archive. It's AxioNyx, so that's the code, simulating mixed fuzzy and cold dark matter. That's the author list here, so it's not only myself and Mateja, but it's actually a whole collaboration, both from Göttingen and in Auckland, also with Christoph Behrens, Jens Niemeyer, and Richard Easter. And I think we went through most of that. So that was kind of our introductory slide. We can see here on the upper left that cold and fuzzy dark matter, which is here only named dark matter, really is indistinguishable on large scales. But then on small galactic scales here on the upper right, we can see this typical interference pattern on the de Broglie wavelength, especially visible here in the halo. And then here in the very center, you can see the core that Mateja was talking about as well. So just to give that a little bit of mathematics, so it's what we simulate actually is the Schrodinger equation with a potential sourced by gravity. So therefore we use the Poisson equation. And then the density really is the absolute square of that wave function. And due to this wave function, and since it mathematically is described by the Schrodinger equation, we see a lot of analogous phenomenology that we are familiar from quantum mechanics, even though it's a classical field. Namely, we have a de Broglie wavelength in that system that is inversely proportional to the velocity, and also a de Broglie time, which is then 1 over the velocity squared. And really all the features, all these interference patterns and granular structure and solitons that we will be talking about here, that's all on the de Broglie wavelength and the time. So that's why this fuzzy dark matter with a mass of 10 to the minus 22 is typically interesting, because as Mateja said, that then for typical velocities of, let's say, 100 kilometers per second, that has a de Broglie wavelength of roughly kiloparsecs, so on galactic scales. And just to complete this introduction, then here on the lower left, we see typical radial density profiles for those halos, where in the outer part, the NFW profile is recovered, but then the central part really strongly deviates from cold dark matter, where we would see a cusp. And here we see this core that is supported by coherence effects from this wave-like behavior.
And just a quick question on that, I don't know if you'll have an answer, but is there like a relatively short, intuitive way of explaining why the Schrodinger equation is the right equation here?
We here investigate a scalar field. More correctly, it's even a pseudoscalar field, but that doesn't really show up in these equations. A scalar field in relativistic cosmology would be described by the Klein-Gordon equation. And then if you go to the non-relativistic limit, that is appropriate indeed for axions, since they are produced via the misalignment mechanism and therefore have very low velocity and really are in this extremely non-relativistic state. You can basically do the non-relativistic limit of the Klein-Gordon equation. And since that is actually the equation for a scalar field, you naturally arrive at the Schrodinger equation being the non-relativistic limit. Yeah, so since these interference patterns then show up on the de Broglie wavelength, you can basically probe these features on different scales. And then naturally, the lightest quasi-dark matter masses have de Broglie wavelengths that are particularly large and therefore can be probed on linear scales with cosmic microwave background or large scale structure. And then with heavier masses, you have to go to more and more non-linear scales. And then with reionization with the UV luminosity function, and so on, and then finally with the Lyman Alpha force. And there was actually an interesting paper just published today on the archive where they pushed this Lyman Alpha limit even further to around 10 to the minus 20. So basically the idea here is that the further you go into the nonlinear regime, on galactic scales, the further you can probe these heavier masses. And by now, fuzzy dark matter research mainly focused on filling this small gap here that you can see, that is then on the higher mass and actually constrained by black hole superradiance from supermassive black holes. And there are already a few studies, for example, Jens Niemeyer and Dodi Marsh published an analysis on the Eridanus 2 star cluster and its stability. And if that is confirmed by numerical simulations, so far it's just analytic predictions, but if that is indeed confirmed by numerical simulations, then this gap here also would slowly fill up. This all here is for pure fuzzy dark matter, so that the fuzzy dark matter is all the dark matter in the universe. So obviously these constraints here would be alleviated if fuzzy dark matter is only a fraction of the full dark matter in the universe. So that gives us another motivation for investigating the mixed case to basically open the parameter space slightly wider.
And is it true that the 21 centimeter edges and above, that's all essentially just the de Broglie wavelength kind of smooths the stuff out a little bit, and then you would expect to observe slightly less power in your power spectrum of all of those observables?
Yeah, exactly.
And then the black hole superradiance, that would be somehow the axion field would be being excited by these black holes that just happen to have the right wavelength?
So the black hole superradiance is a completely different approach, basically. Therefore, it also constrains a complementary mass scale. So if you have a rotating black hole, then due to the Penrose effect, you can have what is called black hole superradiance. So you have an instability in the fuzzy dark matter field around that black hole. The effect is kind of analogous to lasing with an inversion in the states. So also here you get an instability that actually lets a fuzzy dark matter cloud grow around in these mass scales here, for example, a supermassive black hole. Therefore, these experiments are actually particularly interesting because you don't need a fuzzy dark matter particle to be the dark matter. Because what you probe here is really the creation of this cloud, potentially out of no background or a negligible background. And then on the one hand, you have these clouds growing like sometimes it's referred to as this gravitational atom. Because in the limit where the Schwarzschild radius becomes very small compared to the cloud, it really acts like an atom with different states comparable to the hydrogen states in that atom. This process is particularly effective if the Compton wavelength of the fuzzy dark matter particle, if that is comparable to the Schwarzschild radius. So in natural units, if the product of these two masses is 1, then this becomes particularly effective. And then in both other cases, so if the fuzzy dark matter mass is way too light, then we have this atom case. And if it's way too heavy, then it's also inefficient. And so therefore, these 3 orders of magnitude that are kind of excluded here are the 3 orders of magnitude where we have corresponding supermassive black holes.
And the data is literally that we've seen them spinning, right? So we know they can't be losing all their energy.
Exactly. So yeah, we need them spinning, and we need them in different mass bins. So basically the supermassive black holes that we know span 3 orders of magnitude in mass and therefore exclude, or maybe 2 or whatever, but then therefore exclude 3 orders of magnitude in that space. And then the stellar mass black holes would then probe completely different mass scale, much higher than what we consider here. So that would be far on the right of this plot. That brings me to what we presented in our recent paper, where we basically quantified mixed fuzzy and cold dark matter on galactic scales, so in halo dynamics. And we mainly focused on radial density profiles that I also briefly introduced in the introduction. We had a look at the correspondence between the cold dark matter velocity dispersion that in fuzzy dark matter shows up as this granular structure due to the waves. So if we have waves with different wave numbers and wave vectors, then those interfere. And basically this dispersion in the wave vector, so this velocity dispersion, then shows up as the interference pattern in fuzzy dark matter halos and filaments. And then finally, I will also comment a little bit on the solitonic core dynamics, especially the growth that Mateja already talked about before. And we do this using, as you already mentioned in your introduction, adaptive mesh refinement, and then a spectral code on the root grid, which is the lowest resolved grid that spans the entire simulation box, is uniform and periodic, and therefore spectral methods can be applied here. And then on more refined grids, since these are unstructured, non-periodic grids, resort to finite differencing, and then the cold dark matter is evolved by the n-body approach that is already implemented in the underlying NYX code. So that's basically how a typical simulation looks like. So we have this full simulation box where almost nothing happens, and then in the very center we have a small overdensity that we let collapse. So in the main part of the paper, we actually investigate nonlinear dynamics in spherical collapse for mixed dark matter. So here, basically, this very center here, there we see our collapse structure, and then we can zoom into that central part, and we start to see this granules. You can also still kind of see the spherical nature of our initial conditions, but we actually break this spherical symmetry by the non-spherical adaptively refining grids that you can maybe see here. Here you can definitely see the grid structure as well. As you can see, it's non-spherical, and therefore that breaks the spherical symmetry, and we obtain these granules that don't look spherically symmetric anymore. But that explains why I keep talking about spherical collapse, and none of these pictures here look really spherically symmetric. But then here on the lower left, you can really see the granular structure on the de Broglie wavelength, and then this central granule, which is this ground state solution that we typically call a solitonic core, that is really self-supported by the interplay between gravity and these coherence effects. So then just basically after an entire test suite that people can look up in our paper, then the first basically interesting new test that we did was the spherical collapse, first in the linear regime, because there we can really test it against analytic expectations. And here, just for reference, if somebody wants to look it up, so that's the linear equations. For in the top it's fuzzy dark matter, in the bottom it's cold dark matter. As you can see here, it's almost the same, except for this term here that exactly encompasses these coherence effects, and also introduces a gene scale below which gravitational collapse is supported against. So the gene scale being exactly when these two terms cancel. And then on the right-hand side, this here is basically the cold dark matter contribution to the fuzzy dark matter part, and vice versa, depending on the fraction of fuzzy dark matter that we have. So on all the plots that I show here, the fraction of fuzzy dark matter is always color-coded, with blue being no fuzzy dark matter and red being pure fuzzy dark matter, and then the rest cold dark matter. So we investigated this linear collapse, and indeed below the gene scale, actually. So the entire overdensity that we simulated is below the gene scale. So in a pure fuzzy dark matter case, the fuzzy dark matter should not collapse, because it's supported by these coherence effects. And therefore, the cold dark matter density is actually suppressed, or the growth of the central cold dark matter overdensity is suppressed because part of the cold dark matter cannot collapse. And there's actually an analytic solution given here. And we didn't come up with that. So this is well known if you simulate cold dark matter and neutrinos. Actually, then the increase in the cold dark matter overdensity is also suppressed by the neutrino background. So that's the same phenomenology here. And then on the other hand, you can look at the maximum fuzzy dark matter overdensity. So initially I said it cannot collapse, but as soon as the cold dark matter develops a deep enough potential, then indeed this potential can overcome the fuzzy dark matter gene scale, and then also fuzzy dark matter can collapse into that potential well, kind of like baryons collapse into the potential well of a fuzzy dark matter halo. And also here we have a linear prediction for at least the late time behavior that is here shown in dotted lines, and then our numerical results in solid lines. And as we can see here, that it again nicely follows the linear prediction. Here we investigated two different scenarios, namely where initially we have homogeneous fuzzy dark matter, so no overdensity in the fuzzy dark matter part and only an overdensity in the cold dark matter part. Therefore, here with the solid lines, we start from minus infinity, so from flat, basically. But then also showed that the late time behavior is not due to this very artificial test case by also initializing a fuzzy dark matter overdensity, and that would be here the dashed lines. And we can indeed see that initially it immediately disperses because it's below the gene scale. So it's unphysical to be clustered so strongly below that gene scale. So it actually disperses and then oscillates around, and then only in the late time, then it converges to the linear expectations. So let me then come to the more interesting regime, which is then the nonlinear regime, where we fully collapsed the halos. And that's basically the simulation that we also saw at the very beginning, with the granular structure and the core in the center. And Mateja already told us a lot about that. So let me just recap that again with pictures here now. So here on the right-hand side, we see radial density profiles, again, cold dark matter in blue and fuzzy dark matter in red. And as we can see here, these two profiles are always parallel to each other, with the difference always being the initial fraction that we use. So we can see that best here in the middle plot, where we have equal amounts of fuzzy and cold dark matter, and indeed both lines basically lie on top of each other. And then for more fuzzy dark matter, the fuzzy dark matter line obviously is higher, and then for more cold dark matter, it's lower. But so these basically perfectly line, meaning that fuzzy dark matter evolves equivalently to cold dark matter on scales larger than the de Broglie wavelengths. So here, since we show a radial density profile, we average over spheres of equal radius, and therefore average over multiple de Broglie wavelengths. And then since we average over multiple granules and multiple de Broglie wavelengths, the behavior of fuzzy dark matter is the same as cold dark matter.
Yeah, I guess this hasn't been shown before to this level of explicitness, because I guess this bottom plot has appeared before and people have argued, oh, it looks like an NFW profile, but you guys have gone one step further. It looks like exactly the NFW profile you would get with cold dark matter.
Exactly.
Not just an NFW, but the one that would have come if it had been cold dark matter.
Exactly. So that for me, that really is one of the main results. I mean, there have been studies before where the same cosmology was run twice, once with fuzzy dark matter, once with cold dark matter, and then both were overlaid on top of each other. And also those showed remarkable resemblance. But this here, I think is a new quality in the sense that it's really the same simulation, and these lines perfectly align with each other. And then only in the center, we recover this solitonic core. And as Mateja said, so we recover it actually for enough fuzzy dark matter. So as we can see, the lower we get in fuzzy dark matter, here we don't really see this core anymore. And then especially for only a percent of fuzzy dark matter, there's really no stable ground state here anymore. So we conclude that we need at least 10% fuzzy dark matter to produce a stable solitonic core in the center. The other interesting thing is that we can also have a look at velocities in that halo. And that was actually shown previously in a paper by Jan Feldmaat, myself, and Jens Niemeyer, that if you calculate the corresponding velocity spectrum from the wave function. You can actually mathematically show that if you take basically the absolute square of the Fourier transformation of the wave function, then this translates into a velocity spectrum. So this goes by the name of Wigner transformation. So basically we use the Wigner transformation of the wave function and then average over space in order to only get the momentum part of the phase space distribution. And that gives us a velocity spectrum. And as we can see here in those plots, the velocities, even the velocity spectrum that we get is very much aligned with the cold dark matter velocity spectrum that we get immediately from the particle information. So these velocity spectra were calculated from the inner 4 kiloparsecs. So if we come to the right plot here again, then 4 kiloparsecs would be here. So as you can see here, it's really the inner part of the halo. So larger than the solitonic core radius, which is here the dashed line, but inside the virial radius that we mark here with a solid line. So that's the virial radius, that's the core radius, and the volume that we investigate is somehow here in the middle.
So the soliton would still technically be included in that, but just occupies a tiny fraction of the volume.
Exactly. So that is actually the very interesting thing. So Philip Marsh et al. Actually showed that the core radius, so the dashed line here, can be associated to a core velocity given by this simple equation. So again, we can see here the de Broglie wavelength basically showing up. And this core velocity, that is the dashed lines here on the left. And as we can see, maybe not here for the lowest plot, but in general, it is very nicely aligned to the peaks in the fuzzy dark matter velocity spectrum, which shows that indeed the soliton is in kinetic equilibrium with its surroundings. So the atmosphere around that soliton has the same characteristic velocity as the soliton itself.
So you said that the CDM and FDM follow each other. In some of those plots, that doesn't necessarily look like what I would have said. Maybe at the high velocities they do, and you even see this kind of interesting bump at maybe about 40 kilometers per second, and they both have that interesting bump. But at the low velocities, it definitely looks like the fuzzy dark matter is deviating until it gets so small that maybe it's just being overwhelmed. The fraction gets so small that it's being overwhelmed by the cold dark matter.
That is definitely true on a detailed level. I have to admit that. So here I said even the velocity spectra are the same in the sense that they have the same characteristic velocity and at least qualitatively kind of the same shape. I mean, especially here for this fraction, I mean, it's basically perfectly on.
Yeah. Well, so at the two extremes, it looks like it matches, right? Because either the fuzzy dark matter dominates so much that the cold dark matter just has to do the same thing, or the cold dark matter dominates. But the 0.3 and the 0.5 are the two interesting ones, I guess.
Yes. On the one hand, yes. On the other hand, and that actually is better seen on the next slide here in the lower left. That is probably the most technical plot. So what we see here is velocities for different fuzzy dark matter fractions again. The dashed line, the horizontal dashed line here, that's just for reference, that's the virial velocity of the halo. And then we have the fuzzy dark matter and cold dark matter peaks of that spectrum. So we always take here the peak and plot this velocity in this plot here. So here, just for reference, the horizontal line is the virial velocity, and then the diamond and cross, that's the fuzzy dark matter and cold dark matter peaks in the velocity spectra. So we always take here the maximum value and then put it into that plot here. And again, for varying fractions. And as we can see here, for cold dark matter dominated systems, actually both peaks are very close to the virial velocity. But then as soon as fuzzy dark matter starts to dominate and the soliton in the center forms, then these velocities, especially in the fuzzy dark matter part, start to strongly deviate, actually closely follow this solid line, which is exactly this core radius, core velocity relation. So once the soliton forms, it basically creates its own environment and can actually start growing even beyond what is typically considered, where we say that there's somehow an equilibrium between the soliton velocity and the virial velocity that then translates into the famous core halo mass relation. So here we definitely see a deviation from that in the sense that the core seems to keep growing even beyond this simple relation. And that basically brings me to the final two plots where we indeed show this growth of the soliton. So on the upper left, we see the maximum fuzzy dark matter overdensity on a logarithmic scale, where we here see this degenerate initial collapse. And then at some point, and that's actually roughly 1.5 times the freefall time or the dynamical time scale of that collapse. So shortly after the initial collapse, we indeed see the breaking of this degenerate collapse and the formation of a solitonic core. So that really enhances the central density, especially for a lot of fuzzy dark matter. And the growth of the solitonic core can actually be better seen on a linear scale, and now presenting the amplitude instead of the density, and both as a function of the freefall time now. So here we can see that indeed the soliton really starts to grow roughly at 1.5 freefall times. And then indeed the amplitude seems to grow linearly in time. And that is actually something that Dima-Levkov et al. Predicted in a paper from roughly 2 years ago. And this linear increase in amplitude is quantified by these two equations. So the linear increase on the time scale of the condensation time, which Dima-Levkov showed to be proportional to the velocity to the power of 6 divided by the square of the density. And indeed, plugging in the core velocity that we saw before and the central density, then this gives us a scale that very nicely corresponds to what we see. So this theoretical prediction basically is the dashed lines, and the solid lines are our numerical results. And as we can see here, I mean, they deviate around the expectation, but they very nicely align. And what we can see is that indeed, especially for pure fuzzy dark matter, so that's the highest curve here, we have this strong increase. And then for lower fuzzy dark matter, the growth of the soliton is actually suppressed to a degree where there is almost no growth anymore. And that is probably one of the reasons why actually for too few fuzzy dark matter, we don't see a stable soliton forming anymore, because the formation timescale probably becomes larger than the gravitational timescale, and then solitons are constantly disrupted as soon as they start forming.
Can you potentially give an intuitive explanation of, first of all, why it should be linear, and then if you can do that, the second one, why linear with this particular scaling of the slope? Why v to the 6? Why m cubed? Why rho squared?
That's actually in this field of research the whatever $1 million question. So far nobody came up with a consistent theory on that, unfortunately.
This is not empirical, right? Levkov et al. Derived this using arguments. So what were their arguments?
So we have a theoretical understanding for the time scale, but this is really the time scale of formation of that soliton.
And can you give a sort of quickish, intuitive explanation of why those, I mean, the square roots of 2s and pi cubes don't matter too much, but why m cubed v6 rho squared? If
we phrase these terms here slightly differently, then so the velocity always translates into an inverse length scale via the de Broglie wavelength, basically. So this here really is density times de Broglie volume, and then both cubed. So basically it is 1 over mass squared, where mass meaning the effective granular mass, or the mass within one de Broglie volume.
And then one translates that into a time scale the same way one would translate a de Broglie wavelength into a de Broglie period.
Exactly. So then this time scale is basically the relaxation time scale that goes as 1 over mass squared. So I think, yeah, I always view it as a relaxation time scale going as 1 over the mass squared, where the mass here is now not the particle mass itself, but it has actually been also mathematically more sound being shown that here the interesting mass, or the mass that should be that is important for this relaxation, it's not the particle mass, but the mass of these effective granules.
And then the linearity, is that just empirical or?
And then exactly, and then this equation here, so the linear increase in amplitude, that is indeed empirical.
So if any viewers think they've got an idea, there's your, I mean, Bodo called it the $1 million question, but we won't offer you $1 million, just a cosmology talk.
There are a few groups looking at this, including Dima Levkov himself, but so far nobody came up with a consistent theory. So what is seen is, again, that the soliton forms on this time scale, but it is so far unclear why it then keeps growing even on that exact time scale. So I mean, it is kind of the time scale of that problem. So it's probably natural that it somehow also shows up in the growth, but at least the linear growth and amplitude, that for now is purely empirical.
Right. But when you see like an empirical fit that has an exponent to the power of 0.72, you think, well, there may not be any theory behind it, but if it's exactly one, then there must be something that's explaining.
Exactly. So yeah, I think most of us in the community believe that there is some underlying theory for that, but yeah, so far nobody came up with a good theory. Yeah, actually that already brings me to my conclusions, especially for this broader audience maybe. So fuzzy dark matter structure formation is similar to cold dark matter on super de Broglie timescales. We saw that in the radial density profiles. And then in cosmological simulations, the exception then is the cutoff in the initial power spectrum, similarly to warm dark matter, for example. And then I showed on the second slide that the weakly nonlinear probes like Lyman Alpha and so on exclude masses lighter than 10 to the minus 21, but that leaves this interesting mass range of masses slightly heavier than that, and those can then be investigated by their really distinguishing features of fuzzy dark matter, which is this strong stochastic density fluctuations in halos, so this interference pattern on the de Broglie wavelength and de Broglie timescales, and the formation of these stable oscillating solitonic cores in the halo centers. And having a sound understanding of these features is then particularly important for local fuzzy dark matter or for experiments that investigate the local fuzzy dark matter density or rely on those, but in particular so-called haloscopes, which are always sensitive relative to the local fuzzy dark matter density. So it's really important to further constrain that. And then even heavier fuzzy dark matter masses can then be best constrained on these nonlinear galactic scales by solitonic oscillations. That's, for example, what Jens Niemeyer and Dottie Marsh used in their Eridanus 2 paper. Or we can have a look at soliton mergers, gravitational heating and cooling, tidal disruptions, and so on. And those kind of things will then be particularly interesting in the era of Gaia, where we really have a sound understanding of stellar distributions in our Milky Way. And we can start investigating even stellar streams and star clusters and so on, and how fuzzy dark matter could potentially leave phenomenological fingerprints in those distributions. And that basically brings me to my final conclusions that further dedicated fuzzy dark matter simulations like the one we did here are still needed, because there are still a lot of open questions. And Jens Niemeyer actually last week in the conference said that fuzzy dark matter is now at the stage where cold dark matter was 25 years ago. So there's still a lot of stuff.
And there's a code that people can use to do it as well now, a public one.
Yeah.
You've gone into some detail on this already, but specifically what is coming next for you guys?
What I currently work on is more realistic and indeed cosmological initial conditions. So using initial power spectra that really reflect this mixture of fuzzy and cold dark matter. And we're actively working on that. And that's actually almost done and implemented into AxionCamp. And then we can insert these initial spectra into the music code to generate initial conditions, and then insert those into AxioNyx. So that's basically the rough pipeline. And we are already quite far with that. I mean, we still definitely need a few weeks or month, but that's hopefully something that we can even do this year. But so that's exactly one line of work that we pursue in the very near future. Realistic cosmological initial conditions that we can then evolve with AxioNyx to the lowest redshift possible, whatever that is. So one thing that could be also interesting then is Philip Mosch actually investigated filaments and what fuzzy dark matter then phenomenology we have in filaments. So far people mainly concentrated on halos, but we could actually also investigate filaments, so that could be another thing. And then how a mixed dark matter case then affects phenomenology in filaments.
Mateja, do you have anything to add about where to next?
Yeah, I'm actually quite interested in how fuzzy dark matter heats the stellar clusters. So that's one of the things that, Dodi and Jens Niemeyer investigated analytically, but it would be good to have simulations. I mean, there are some simulations of that by CU Schwabe, where they just consider a cluster inside a soliton, and then with a stripped halo or without, so with the proper halo, and look into these things, and maybe like more detailed analysis of this would be interesting. Also, just by heating by these granules around the soliton, not just by the soliton. So yeah, in the future, that's something I want to look at. I mean, baryons, including baryons into AxioNyx, is also something we want to eventually work on. Although it requires a bit more of infrastructural work, so it's not, I mean, a near future thing, I think.
Yeah. So with baryons and AxioNyx, and we can comment on that. So the hydrosolver is already implemented in there and works perfectly fine. And there are already stellar particles in the code, but what is still missing is actually producing them, and then all the stellar feedback routines and so on. They were in the original NYX code, but that got basically now we have a NYX 2.0, and in that new version of NYX, these routines are not yet implemented. So that would be the hard part, to reintroduce all the feedback routines.
And I guess another thing that might be in the intermediate future is all of these constraints below 10 to the minus 21 electron volts that rule out, I guess in the language of your paper, they rule out F equals 1, could then be turned into constraints in a two-dimensional space of M and F.
Exactly, yeah. Those can then be also reconsidered. There, especially the Lyman Alpha constraints, I think, are most important and can then be further constrained with codes like ours. I mean, on even larger scales, you don't even need those codes if you just probe the linear scales with a cosmic microwave background, for example, then you don't even have to use those numerically expensive codes. But for the Lyman Alpha forest and predictions in that forest, that could be really interesting.
So lots of uses for your code. Okay, so the last question I'll ask you each individually. Outside of your own research, what do you think is the most interesting thing in cosmology at the moment?
Beside the H0 discrepancy, which I would really like to know where it comes from. Besides that, because that may be the most interesting thing, I really like all these gravitational wave discoveries and the whole field and where it's going, because we can learn a lot about the progenitors, about the black holes, the possibility that they are primordial, and just stellar stuff that we can learn from that. And even all this multi-messenger stuff that teaches us about constraints on the beyond GR models. I think that's really fascinating.
Yeah, okay, I guess that's really the hottest topic in cosmology. So I guess everybody's interested in that. Maybe to add something different, I think also all the high redshift stuff, especially now with James Webb, for example, and WFIRST. So really capturing the first halos at high redshifts around, I don't know, 10 maybe even. I think those will really be interesting, especially if you're considering warm dark matter or fuzzy dark matter, where you have this initial cutoff. That should be really nicely probed by the existence or non-existence of these very early halos. So I'm really excited about these future experiments that always seem to be 2 years in the future, but maybe at some point they will actually be realized. And I think that will be a huge step forward.
Thanks everyone for watching. If you like this, please do subscribe and click the bell to be notified of all new videos, and click like to help the algorithms. And if you have any questions or comments, leave a comment below. And while you're here, you can watch another video. Maybe the most relevant video would be Jurek Bauer's video. He's a PhD student in Göttingen where Bodo is, and he gave a talk on how these ultralight axions have already been constrained. So check that out. And thanks again, Mateja and Bodo, for the very interesting talk.
Yeah, thank you very much for having us.
For inviting us.